All right, so far we've looked at the principles of work and energy, how they relate to kinetic energy, which is the energy of motion of a mass on a level surface, 1/2 mv squared equals our kinetic energy. We also saw that our gravitational potential energy is equal to mgy. We saw that work done is equal to the integral of f dot dx. If the force changes over the displacement, that's equal to the change in energy, which is equal to the change in kinetic energy plus the change in potential energy. And then we saw that if the external force is equal to 0, this is our special case. If the external force is equal to 0, then the work done by external forces here, this is work done by external forces, is 0. And this means that we have conservation of energy. 1/2 mv naught squared plus mg y naught equals 1/2 mv final squared plus mg y final. Now this is only valid if there's no external forces acting. And we have to adapt this if there are external forces in the problem. But we might ask then, well, isn't gravity an external force? The answer is no, because we change the potential energy against gravity by our external force. So gravity is considered an inward force. So if we just have a problem, say, where we have a mass swinging around and round in a arc-like path, like this, then we could say that this is a closed system. And the system is not just the mass, but also the Earth. And so the external force then is not coming from the Earth. But if I were to hit this thing, that would be an external force, because that would be coming from the outside. But the inside forces are the mass and the Earth together. So that's a very important point and can be a subject of confusion when we deal with this. But we're not considering gravity to be an external force, so that this relationship works under the influence of gravity, because gravity is a part of the system. The Earth and the mass are the system. So it's important that you keep thinking about that until that makes sense to you, and that you don't make a mistake that has to do with trying to calculate, for example, the work done by gravity in one of these expressions. It won't be valid the way that we're handling the problem here. Now, so far, this is a kinetic energy and a potential energy term before and after, but there are other kinds of energy too. And we're going to be adding more and more terms to this expression as we go. But the next one I want to do has to do with the spring force. And so here, what I'm going to do is I'm going to take a spring, and let's neglect the mass of the spring itself, and we'll hold it up so that the spring has a natural unstretched length. Okay, so we'll bring this thing down to here, and so this will be our unstretched length of the spring. So this is with no forces being applied to the spring. I'm going to call this x equals 0 at the unstretched length. And I'm going to hold this thing solid up top, and I'm going to add a 0.5 kilogram, or 500 gram mass to this. So what we're going to see is that the system stretches so that there's a spring force that is exerted upward like that. But we also see that this mass is in equilibrium, right? Because the spring force and the gravity force are equal and opposite. So mg has to equal in magnitude and be opposite in direction the spring force. And so then I can draw this distance here as being my stretched length, which I'll call x. So x vector then is going to be my stretched length. That is associated with the spring force. And in equilibrium, we can say that the force of the spring equals minus mg equals 0. So this is just the sum of the y forces equals 0. Now the question then is, well, what is the spring force? Well, the spring force, F, and this is what's called Hooke's law. Hooke, by the way, was a kind of a crazy guy from the time of Isaac Newton that was always causing Newton a lot of anxiety. Newton didn't like criticism, and Hooke really had a big ego. And so Hooke antagonized Newton, and Newton actually withdrew from the scientific community until he was brought back out into the open by Halley when he was trying to determine the inverse square law of gravity. And that's when Newton decided to invent physics. Okay, but Hooke has quite a history, not all of it good, but here's his law, F equals minus kx. So this is our spring force, and this is our spring constant, k. And this is our displacement. The negative is an indication of the fact that the displacement and the force are always oriented in opposite directions in terms of the vector. Okay? And so the force is always what we call a restoring force that tries to bring the stretched spring back to its zero equilibrium position. And then x, of course, is the distance from the unstretched length to the point at which the spring has been stretched. And so the force then gets bigger and bigger as the x gets bigger until finally we reach a point where the force is exactly the same magnitude as the weight. And then that's when we reach static equilibrium. So in this example then, this is not just one particular example of how springs work, but it's a really common way to figure out the spring constant. Because if we know what the weight is of the object, and we know the displacement, if we can measure that displacement, then we can figure out the force. And so a really big spring, like the kind of spring that would hold up the weight of your car, might have a value of, say, 20,000 newtons per meter. So let's have units of Newton per meter, because this has units of newtons and this has units of meters. So the constant oftentimes is where you put all the units to make the left and the right-hand side of the equation dimensionally consistent. And so for a really big car spring, you might have k equals 20,000 Newton per meter. For a little delicate watch spring, you might have k equals 0.01 Newton per meter. And then medium-sized springs, like the ones that we're using in lab here, might be a few tens of newtons per meter. And we'll see, because we're actually going to calculate this in a second. And so we'll find out if my order of magnitude estimate is correct. Unfortunately, because we're in the physics lab, we always have a meter stick. When I'm in the biology lab, a lot of times I can't find the meter stick. And so then I'm in trouble. But here, we're in good shape. And so we'll measure this distance here, and make sure we're not on the inches side. And so this will start it from, let's see. It's funny that we're running into this problem. Okay, this is 83 to 51. So that would be 22 centimeters would be x, or that would be 0.22 meters. Okay, and we know that the mass is equal to 500 grams, or 0.5 kilograms. So we can plug that into this expression, and we get kx equals mg, or k equals mg over x, which is 0.5 kilograms times 10 meters per second squared, divided by 0.22 meters. Which gives us 22.7. Newton per meter. Okay, so this is a way then of measuring how strong the spring is in relationship to the amount of weight that we might want to hang from the spring. And so if we were to plot this up, in terms of force versus displacement, it looks something like this, F versus X. And here we'll look at the magnitude of this so that we don't have to worry about negative signs. We know that the force points in the opposite direction from the displacement. So we'll do the magnitude of F versus X. And we see that the slope here is the spring constant. Okay, so that'll be true up to a certain point. And this is the point which we could call X max. And that's the point of maximum possible deformation of the spring. Once we get to that point, then it becomes nonlinear and we get permanent deformation. And it starts taking less and less force to create more and more displacement once we're past that point. Okay, and so this is our straight line, and we'll stay within the straight line relationship for the examples that we'll be doing. So the question that we might want to ask is then, how much work does it take to stretch this spring from x equals 1 meter to x equals 2 meters? And let's say that in this case, just to make the numbers a little easier to work with, that k is equal to 10 newtons per meter, which is still in the same ballpark as what we were looking at in this last example. Now, in this next example, although we might use a vertical mass hanging from a spring in general to figure out the spring constant, here we can eliminate gravity by just moving this thing along a horizontal surface. So here, let's call this x equals 0. And then first, we'll start out with x initial at 1 meter. And then we'll start from here and we'll pull it to x final equals 2 meters. So we'll have to start out with a smaller force here This will be our external force that we need to, not the spring force itself, but the force that's being applied against the spring that balances out the spring force, which tends to want to pull it back. So to slowly pull the spring to this new position, we've got to slowly add more and more force. Okay? And so that is, because that force has to be exactly the same as the spring force, that is our external force here that we're applying. So that's the work that's being done by an external force, the force of us pulling on the spring. Okay? And so that'll pull it out this way. And so we'll go from x equals 1 to x equals 2. Okay, so how do we do that? The work required, in general, is the integral of f dot dx. Okay, and so here, the force is always in the same direction as dx. Our increasing x is in the same direction as the force. So this is just equal to the integral from x equals 1 to 2 of kx dx. And let's do it just x initial to x final, and then I'll plug in. So we'll get a general expression, and then I'll plug in what x initial and x final are. So the integral then of kx dx from x initial to x final is just going to be 1/2 kx squared, evaluated from x initial to x final, or 1/2 kx final squared minus 1/2 kx initial squared. Okay, so this gives us then the work in terms of the difference in 1/2 kx squared. So let's call the potential energy of the spring, we'll define it in the same way that we did before, so that the change in energy is equal to the work that's done. And so it's just a convenient definition for energy. We're saying that because the difference in 1/2 kx squared is equal to the work that's done, we'll say that that energy must be 1/2 kx squared. And then it's the change in spring energy. Okay. And so if we do that here, then we can figure out what the work is that was done by that force in terms of, well, this would be 1/2 k times x final squared minus x initial squared, factoring out the 1/2 k from both terms. And that'll give us 1/2 times 10 Newton per meter times x final. That's 2 meters squared minus 1 meter squared. So that'll give us 5 times, this is 4 minus 1 is 3. Or 15 joules. And so that is the amount of work that we do. And that's also the area under this curve. Okay, so the work done is the area under the force versus displacement curve for this problem. Here we have a distance-dependent force, which is equal to kx. So we can integrate that, and that gives us the change in the spring energy. We could double check that this is in fact the area under the curve by just figuring out the area of this rectangle. So that's going to be, well, here, as we apply this force, F is kx. So at this point here at 1, this would be F1 is equal to 10 times 1. And then here, F is kx. So F2 would equal 10 times 2 kx in both cases. Okay, so here this is going to be 10. So 10 is the height, and the base is 1. So the area then is equal to 10 plus the area of this triangle, which is 1/2 the base, which is 1, times the height, which is 10. So that gives us 15. So that's exactly what we've got there. And we can see then that the area under the first force displacement curve is the same thing as the work that we do, which is the change in the energy that we get by integrating this expression. And so this means that we can, if we have springs in a problem, we can expand our work-energy relationship to include the springs. And we can say that the total work done in a problem that has springs in it too, as well as maybe potential and kinetic energy, would be work done by kinetic energy changes plus work done by potential energy due to gravity changes plus work done by potential energy due to spring changes has to equal the change in kinetic energy plus the change in gravitational potential energy plus the change in spring potential energy. Or, on the left, this is just the integral of f external dot dx from x initial to x final equal 1/2 mv final squared minus 1/2 mv initial squared plus mg y final minus mg y initial plus 1/2 k x final squared minus 1/2 k x initial squared. So this is the change in spring energy, this is the change in gravitational potential energy, and that's the change in kinetic energy. Okay, so we're getting a more expansive expression for the total work. Now, if there are no external forces, this also gives us an expanded energy equation. If the external forces are 0, then we have 0 on this side equals all of this stuff. Or we can take the initial terms and bring them over to the left-hand side. That gives us 1/2 mv naught squared plus mg y naught plus 1/2 k x naught squared equals half mv final squared plus mg y final plus 1/2 k x final squared. So this is the initial kinetic energy. This is the initial potential energy. This is the initial potential energy of the spring. And then on the other side, we have the total final energy, which would be the kinetic energy final plus the potential energy final plus the potential energy final for the spring. So this is now our expanded energy equation. And we can use this expanded equation with springs, which is what I'd like to do in the next example. What we've got here, you can see on the data projector, is a loaded spring. Okay, and so we have displaced the spring by 20 centimeters from its unstretched length. Okay, and let's assume that what we've got there in the middle is the unstretched length. So that's our x equals 0 reference position. So we're going to squeeze the spring by that amount. The spring has a spring constant of 500 newton per meter. So then we launch that. The potential energy of the spring is turned into kinetic energy. Then the kinetic energy is turned back into potential energy as it goes up the incline. So for this problem, let's find the distance up the incline. I'll redraw it down here. We've got our loaded spring. This is our initial position. So here, this is going to be our x initial equals 20 centimeters, or 0.2 meters. Then we launch this thing so that all of that potential energy turns into kinetic energy. Say there's no friction yet on the surface. And then just to make this a little easier to work with, I'll make this a 30-degree angle instead of a 45, as it was in the data projector example. And so let's find the distance d that it moves up the incline before coming to rest. Okay, so going back to our energy equation over here, we see an awful lot of terms, but there's no external force. So you go, well, if there's no external force, then what pushed it to this point to begin with? How did it get to this point if there's no external force? Well, that's true. But we're not counting that. We're saying, let's start here. Let's say that somehow we get it to that point. So there's no external force to load the spring, but you'd have to do work to load the spring. Okay? But once we get it to that point, let's say that that's where we start, and that this is where we finish. This is our final point. That means that there's no external forces in the problem looked at over that interval of time between when it's released and when it finally stops. So that means we can use the energy equation for this. And so in the initial position, we have an initial velocity that's equal to 0. Because it hasn't started moving yet until it gets to here. That's when the spring has unloaded its energy. So by the time it gets to there, it's moving. But at this point, not moving. But we do have an x naught of 0.2 meters. Okay? And we have no gravitational potential energy because we're at the bottom point of the path. So we'll call that y0 equals 0. Remember the way that we were doing this before is we were measuring from some reference position what the initial and the final y are. So here we could call this y final. And although we don't know what that is, we can certainly write in terms of our unknown d, which we're trying to solve for. And so we do that here. That's going to be d times the sine of 30 degrees. So that's our y final position, but y final is 0. So now going to the energy equation, it seems almost too easy because we can get rid of almost all of our terms. Look at this. The initial velocity is gone. The y naught term is gone because y naught is 0 at the bottom. So we only have the spring energy at the bottom. Now, we do have kinetic energy in the middle. So we could go from here to there to figure out the kinetic energy. But why bother? If there's no friction, we'll just figure out the potential energy up here. So it's going to go, and if we follow this progression, imagining again the water as energy, then we start out here at the beginning with all spring potential energy. Then this is going to turn into, by the time that the spring's been released, all this energy now is going to be kinetic energy, but I haven't spilled anything. Now, if I spill it, that would be like friction, because that would take away energy from the system. So if I spill some, that'd be like a more realistic situation where water is spilling on the ground, or energy is heating up the ground and also heating up the mass. But now, that kinetic energy is going to turn into gravitational potential energy until all the kinetic energy is gone at the point when it reaches the maximum point. So now it's all gravitational potential. So I like these water analogies. And that's why I always like to make energy positive. You can make energy negative by calling this value here a negative value for y naught, but then how do you pour negative water? Okay, so here, 1/2 mvy v final squared is 0. mgy final, this is the only term that remains, and the spring energy has all been released. So it doesn't have any spring energy anymore at this point. So what we're left with then is just a relatively simple equation. 1/2 k x naught squared equals mg y final. Now, one thing that we're going to need to know for this problem is what is the mass. Let's say the mass is 2 kilograms. And we have the spring constant. K was equal to 500. But we need the mass here, whereas we didn't need it in the other examples that we were looking at with the energy equation before, because the mass canceled. Now, when we were just dealing with kinetic and potential energy, and we didn't have the spring energy in there, we had common factors of the mass all the way through. But now we don't have that anymore because the spring energy term doesn't have any masses in it. Okay, so that doesn't cancel. But that means that the mass needs to be known. We can't just go through the problem and not care what the mass is. We have to plug it in. And then we can also plug in, because we're actually solving for the distance up the incline, we can plug in for y final d sine theta. That gives us 1/2 k x naught squared equals mg d times the sine of 30, which is 1/2. Okay, and so that's equal to y final. That's what we have here. Y final is d sine 30. So now we can just solve this for d. The 1/2's cancel on both sides of the equation. So d equals k x naught squared divided by mg. Okay, so that'll be 500 Newton per meter times 0.2 meters squared divided by m, 2 kilograms times 10 meters per second squared. And that gives us 1 meter. Okay, that's good. 1 meter, that's how far the mass will move up the incline. And so that's without friction. Now we might ask, well, what if we've got friction? That's a more realistic problem, much more realistic. But let's take it a little easy on ourselves and say no friction on this surface, but on the incline, let's say that mu k is equal to 0.5. Now let's find the distance up the incline before coming to rest with friction. Okay, well, we're going to need to, because friction is an external force. Okay, so what we're going to need to do here is go back to our original expression for work and energy. Say that work, in general, is equal to the change in kinetic energy plus the change in potential energy plus the change in spring potential energy. And so in this case, the work done by external forces is the work done by friction. Work then is going to equal the force of friction times the displacement. In this case, that's going to be d. Okay. And then that's going to be negative. Okay, because it's going to be times the cosine of 180. Force of friction times d times the cosine of 180 is going to equal minus force of friction times the displacement. Okay, so if we want to set this thing up like a conservation of energy equation, but leaving that work in there, what we have then is just minus the force of friction times d equals 1/2 mv final squared minus 1/2 mv initial squared plus mg y final minus mg y initial plus, if there's springs too, 1/2 k x final squared minus 1/2 k x initial squared. And so what I'm going to do is I'm going to move the FD over to the right-hand side of the equation. And I'm going to write this just like I did the energy equation, but with this extra term. So if I do that, we can rewrite. And what that gives us then is 1/2 mv naught squared plus mg y naught plus 1/2 k x naught squared equals 1/2 mv final squared plus mg y final plus 1/2 k x final squared plus fd. But what this is here is just the absolute value of the work done by friction. Because it's negative on the left-hand side, and so that means that it's actually taking away energy from the initial state. And so you could put it as minus FD over on this side and just say the work done by friction. And either way, it's going to be equivalent. So here, I like doing it this way. Some people would disagree with this as being the most clear way to do it, but if you use the water analogy, which I like to do, then we start out with a little bit of initial energy here. Then that energy goes into final energy, but some's been lost. Okay, so that's like the work done by friction. That's the energy that's lost. So there's less final energy because some of it was dumped down the sink. And so you can either write it that way or put the work done by friction over here on this side, but then you have to remember to make a negative. And so I'm going to do it this way. And so that is an application of the work energy expression with only one external force acting, which turns out to be fairly common in these problems, is that you just have friction. And friction is kind of hard to get away from. So it's unusual that you wouldn't have friction in a problem like this. Okay, so basically it's just our energy equation with plus the absolute value of the work done by friction written as our last term. If we just have a problem where only one external force is friction. But in general, we can write it like this. Say the work done by all external forces, work total, plus this equals that. And so that's something that's always true no matter what kind of external force acts. That if only friction acts, you can write this as the work done by friction, but then it's negative, which is the same thing as just adding it to this side of the equation. Okay, so given that we have this equation, which is similar to the last one, let's solve this problem one more time. Let's start out with an initial stretched, this is a compressed spring distance. Now, compressing or stretching, as long as it's the kind of spring that will compress, is going to give you the same value for the spring force, and so therefore the same value for the work. So it doesn't matter whether the x naughts here or x finals are positive or negative, because they're being squared. So it's the same amount of spring energy whether you compress the spring or whether you stretch it. Okay, and so that's something you don't have to worry about. And so let's go back and see which terms are going to survive and which terms we need to be concerned about here. Well, initially, we've got no kinetic energy, no potential energy, so we just have spring energy, 1/2 k x naught squared equals. And then in the final state, we have no kinetic energy, no spring energy, but we have mgy final, just like before, but now we've got this extra term, which is the force of friction times the distance up the incline. Force of friction times d. Okay? And so that's the work done by friction. So we have spring energy turning into gravitational potential energy, and this is energy lost, plus the energy that's been dumped down the sink. So think about that. Make sure that that makes sense to you. And then we can go ahead and we can solve for d, which is the distance up the incline. So here we've got 1/2 k x naught squared equals mg times d sine 30 plus the force of friction. Now let's be careful here. This is the coefficient of kinetic friction times the normal force. But we don't want to just automatically think the normal force is mg, because it's not. The normal force we have to get the same way that we did before. This is the mg. And so the normal force is mg cosine theta. So you need the sum of the y forces is 0. And that gives you up the incline. And so this is your xy coordinate system on the incline. So that's going to be f normal minus mg cosine 30 equals 0, or f normal equals mg cosine 30. And so that's what goes in here. Okay, so that's the force of friction times the distance. Okay, or plugging in for the force of friction, we get mu k mg cosine 30 times d. Okay, so now what we have essentially with a known value for the coefficient of kinetic friction, 0.5, is one equation and one unknown in d. So we can solve this for d. So that's going to be d times mg sine 30 plus mu k mg cosine 30. Or we can write this as mgd times sine 30 plus mu k cosine 30. Just simplifying the algebra a little bit. So that then finally gives us d equals 1/2 k x naught squared divided by mg times 1/2 plus 0.5 times the cosine of 30 is 0.866. Okay, now remember what answer we got before. It was just k x naught squared over mg, and the 1/2s cancel. But now that we've got friction, this should reduce the value of d by increasing the denominator. So I'm expecting a number now. Remember before we got 1. So I'm expecting a number now that's going to be less than 1. If you don't get a number that's less than 1, make a minus sign here. Maybe you forget here. Go, oh, this is negative friction, so I put in a negative value there. They give you d that's greater than what it was before. So you would know that something's wrong if you are able to examine the problem and see what a reasonable answer is. Okay? And so here we'll plug in. Let's finish this up. mg. Let's just write it one more time. So it's going to be 1/2 times 10 times, I'm sorry, that's 500 for k, this problem. 500 Newton per meter times x naught, that's 0.2 meters squared, divided by 2 kilograms times 10 meters per second squared times 0.5 times 1 plus 0.866. And calculator on first before I do that. That gives us 0.535 meters. Shouldn't have taken that long. Sorry about that. And so we see then that that's less than 1 meter. And the reason for that is that here we're multiplying by a number that's almost 2, okay, in the denominator. So that's cutting because of friction, that's cutting the distance that we move up the incline by almost a factor of 2, because friction took away a lot of that energy, and the friction destroyed that energy. Well, it didn't destroy it, but it turned it into a different form. It turned it into heat, turned it into sound, turned it into a lot of other things that we'll deal with later when we get to the section on thermodynamics.